So because I didn't want to make the combined loading calculation overly complicated for mechanics material class, so I try not to put too much emphasis like you have to give me exact sign of the shear stress. But since some students ask how to identify the sign for shear stress for this combined loading situation, so I think I recorded this video just to help you guys if you really want to know the sign for shear stress in this complicated situation. It's not required in the exam. In the exam, if you can give me a magnitude, it's considered as correct. But if you are interested in the sign, so here I use the example problem, homework problem as example here. The first one is this example problem in class. And if you look for the cross section, if you look from this side, and this is the cross section. So y-axis, z-axis, y-axis, z-axis for the cross section. And our ABC is on this side. So the shear stress is caused by the transverse shear. And I only put as tau because, well, I didn't want to make it too complicated. But now let's say if you really want to know the sign, shear force is upward. So shear force is upward. And we know that, well, A and C are 0, but B, the shear stress should also be upward. And for the stress component, if we put the subscript should be on the x-plane. This is x direction, cross section is on the x-plane, and in the positive y direction. So this one is positive at point B. A and C are 0. So this is a sign for shear stress in first example. In the second example, very similar. For the point H, we take this, let's say we look from this side and this is cross section. And cross section, this is the y direction, this is z direction, y direction, z direction, right? And H point is on the top and at the middle point. And for the shear stress, it is caused by, well, for this one, it's 0. But for this one, 2.5 is maximum because in terms of 2.5, this is at neutral surface. And so now this force is in the negative z direction. So this is the tau xz on the x-plane in the negative z direction. Positive plane, negative direction. So the sign of this shear stress should be negative. So, but as I said, to avoid a lot of confusion in the class, I only calculate the magnitude, and it does not affect our final calculation for finding the maximum and the minimum, because if you have negative, basically you have a diameter point like this, and you have same more circle, same maximum minimum principal stress, same maximum shear stress. For this one, it's a little bit complicated because this one, the shear stress generated by transverse shear force and generated by torsion, they're in different direction. So for this one, I actually, in my solution, I actually used the correct sign convention, not only the magnitude. So here, for this cross section, if I look from this side, and this is the cross section, and y, z, this is the coordinate of the cross section. And for the transverse shear force, P2, it will generate a transverse shear stress. It will generate shear stress at K, but at H it's 0 because it's top point. And for the torque, when you have a torque rotating this direction, same thing on the cross section, it also rotating this direction. So for the shear stress generated by torque, at H point it should be this direction, and at K point should be in this direction. So for the subscript at H point, it should be on the Z plane in the, X plane in the positive Z direction. So positive, this is positive. And for shear stress caused by torque, at K point, it's on X plane, negative Y direction. So this one should be negative, and this one should be positive. So here you need to have one is positive, one negative. So of course you can still the same. You can calculate only the magnitude of these two, but you need to realize that the shear stress generated by torque and shear stress generated by transverse shear, they should be opposite direction. So in the end, when you calculate tau xy, you need to use, let's say you only calculate the magnitude of these two. So you use this magnitude minus this magnitude, and in the end, you get the magnitude of the combined shear stress at K point. And once you have this 52, this magnitude, you put in the Mohr circle, you get the same result. So this is for, and I think this is the only problem that involved the shear stress from transverse shear force and shear force in the torque, and they're in the opposite direction. So this one you need to be a little bit careful. And for combining these two, it's okay if you only have magnitude, but if you want to be exact, you can have this one, the positive, this and negative, of course. If you only have, in the end, if you only have magnitude of these two, let's say in your exam, you only have magnitude of these two, and you get, you know that you understand it's in the opposite direction, and you get 52.5, you are considered correct. And Helmer problem, again, cross-section, oh, okay, it's here, ABC, cross-section, and y-axis, z-axis, y-axis, z-axis, and ABC is at this 3 point. So the transverse shear is caused by this 500, because this one we also cause transverse shear, but ABC, they're all 3 points there on the top surface, so they're 0. The only non-zero is caused by this 500 and at B and C. And B, sorry, at A and B, C is the top point. And this one, the shear stress is on the X plane and in the positive Z direction, right? Because force is in the positive Z direction. So is positive plane, positive Z, and shear stress component should be positive. So this is a homework 1. And homework 2, again, HK. This is a cross section. We take cross section from here. And this is a cross section. And the coordinate, since this is the Y is here, and this is the X here on the cross section. And for the shear stress, it can be generated by torque, it can be generated by transverse shear. So let's first check the transverse shear, because this is 600 and H become top point. So H for the transverse shear is equal to 0. At K point is not 0 is maximum. At K point, K is on the neutral surface in terms of this transverse shear. And it should be downward. So for this component, it is on the positive Z plane, this is Z direction, positive Z plane and negative Y direction. So this tau ZY should be a negative value in terms of our coordinates. And the next one, we check the torque. So torque, we know that it will rotate our structure in this way. So in terms of the cross section, rotating this way. So we know that the direction of shear stress at H point should be like this, and at K point should be like this, right? And for if you want to know the sign for these two stress components, first put a subscript. Is both of them are on Z plane, of course. At H point is in the X direction, positive X direction. So this one is positive plane, positive direction. And this one, again, positive plane, negative Y direction. So this one is negative. So both these two are negative, but it is okay if you only calculate the magnitude of this one and the magnitude of this one. And we know that they're in the same direction. So in the end, the combined shear stress caused by torque and caused by transverse shear, you just add these two magnitudes. So let's check the solution. At point, so you can see here, I calculated the magnitude. Oh, this one, it is positive. So yeah. And at K, again, magnitude, you know, it is in the same direction. This is the magnitude of combined shear stress caused by the torque, caused by the transverse shear. So, and of course, if you really want to go fancier, you can put the subscript tau zy. And you have a negative value here, you have a negative value here, and in the end, you have negative 16.5. And then in the end, it does not affect our Mohr-Sokal and maximum principal stress, minimum principal stress, and maximum shear stress calculation. The final calculation will be the same. So my point is that it's okay. You can just you can forget about like subscript with tau x, tau xy. You don't need to really write it down on the for the exam. You just simply calculate magnitude that, but you need to know if it's the same direction or opposite direction, because same direction just simply plus these two magnitude and opposite direction. I just showed that example problem. I think requirement is this level for the exam, but if you really want to go fancier, like I want to know the accurate sign and the subscript for each shear stress, you can go as the way I just explained. Put subscript and use the second tensor to define the sign for each stress component. So I feel like this might be interesting because if you go to more advanced class, it does require you to have the subscript and the correct sign for each component, but it just in our mechanics materials I don't require. So this is all I want to say based on the question asked during the class, how to determine the sign of the shear stress.